Hey everyone, I want to go over the Unit 4 FRQs on probability. And here's the first one that was posted. This was from the 2011 exam, question number 2. It gives you a two-way table of political party registration by gender for 500 registered voters in Franklin Township. And we've seen many of these two-way tables. We've calculated marginal distributions. That would be the totals in the columns and the rows. We've calculated probabilities out of the total from within the two-way table, and we've also calculated conditional probabilities given a two-way table. And that is what the first one is. It says given a randomly selected voter is male, that means we're focusing on this row. So everything in this row. What is the probability he is registered for party Y? So this row total is my total, and then party Y was 48, so 48 over 200 gave us the probability a given male is registered for party Y is 0.24. And that is all you needed to be essentially correct. You needed the correct conditional and showed the work. So enough work here was probably the fraction or this conditional statement with probability. So you didn't need both. You needed one or the other, and then that correct calculation. You were partially correct if you did the opposite conditional. So instead of party Y given male, you did male given party Y, you still got a P. Or you were correct or partially correct if you got a 0.24 with no work. And then neither of those you were incorrect. Part B, among the registered voters of Franklin Township are the events male and is registered for party Y independent. So from way back when, to show independence, you would just show the conditional. I think this is on the formula sheet. Probability of A given B has to equal the same as the probability of A. So regardless if B occurs or not, those probabilities had to be the same. Well, we already calculated a conditional in part A. We calculated the probability of party Y given male, and we got 0.24. So in this one, you really only had to find the probability that you were in party Y. So let me go back to show you where that 0.336 came from. So in the table, to be part of party Y, that's 168 over 500. That is where this 0.336 came from. Those are obviously not equal. So you could stop there and say that the events being male and party Y are not independent because those probabilities were not equal. And the scoring guide, so you were essentially correct. You do all three of these things. You had to have the values whose inequality implies a lack of independence. So you had to say that they were not independent. And then you had to have the correct computations, a statement, which I had here, and then made sure you say they're not independent. So you simply couldn't have stopped. Like if you just put this, you would have been partially correct. Part C, I'm going to go back to the actual problem. Part C was very tricky, especially in the wording. So it says one way to display the data in the table is to use a segmented bar graph. We've made tons of these. The following segmented bar graph constructed from data and party registration of the Franklin Township table shows party registration distributions for males and females in Franklin Township. So these sections of the bar came from dividing the total of that party over the column total. So the sections of the bar, the first section of the female bar came from 60 over 300. The next one came from 120 over 300, and then 120 over 300. And then same for the males, 28 over 200. The next segment was 124 over 200, and then 48 over 200. So that's where these bars came from. And then they go on to say a different township. We have no information on Lawrence Township. The proportions of all registered voters for W, X, and Y are the same as for Franklin Township. And I'm going to stop there. That means in this table, these proportions, 88 over 500 is the same for Lawrence Township for party W. 244 over 500 is the same for party X in Lawrence Township. And 168 over 500 is the same for party Y in Lawrence Township. So that's what that first statement means. And then it goes on and says, party registration is independent of gender. That means that regardless of gender, those proportions are the same. So males, or the probability you're in party W given male is the same as the probability you're in party W given female. The probability you're in party X given male is the same as the probability of X given female. All those conditionals are the same as those parties in Franklin Township. So to create the bar graph now, just knowing they're independent, each of these segments that are created in the bar graph are going to be the same length. So these bars are going to look exactly the same. It's how do we find those probabilities? Well, I kind of already did it for you. If I go back to the two-way table, the proportions are the same. So proportion 88 over 500 is the same for males and females over in Lawrence Township. The proportion for party X, 244 over 500, is the same in Lawrence Township as it is for Franklin Township for males and females, and so on. So when I create my bar graph, and I'll send you these individual solutions, my bars, this 0.176 for both, that came from doing the 88 total divided by 500, the total of all voters, because the proportions are the same. It doesn't matter about the people in the town or in the township. It's that proportion has to be the same. So for males and females in Lawrence Township, the proportion who favor party W is 88 over 500 or 0.176. So that's the first segment in both of my bars. And then same with X and Y. So for party X, 244 over 500 gave me 0.488 for males and females. And then to graph that, segmented bar graphs are like cumulative graphs. So 0.176 plus 0.488 goes up to about 0.6 something something. That's where my bar ended here. And then same when I add my last probability for party Y, and that finishes out my bar to a total probability of 1. And then scoring, I think I got a P on this one. Let's see. You're essentially correct if the response shows the same conditional distribution of party registration for both males and females. That means both of these bars look the same. Or you list both of these probabilities. And includes the following two components: correct proportions for each party. I have that. And correct labels. That's where I'm going to lose points. I labeled it down here in my calculations. I'm not sure if that's enough. I probably should have put W, X, and Y in each of these bars. So I think I would have been partially correct, which is better than nothing. So partially correct says you show the same conditional distribution. That's what I did. But you only include one of the two components. So I forgot to include component 2. So I lost a point there. So I would have been partially correct on that. And then total scoring, we've done quite a few of these already. To figure out your total score on the AP exam, you would total up whether you were essentially correct and partially correct. So I would have been here. I would have been EEP. So I would have gotten a 3 on this question. And again, some of these are tough with how much information do you really need to show, because sometimes showing too much is not a good thing. The second FRQ I posted was much easier than the first. It was just kind of basic expected value problems and then doing a probability distribution. So here was a game. A local arcade is hosting a tournament where you play an arcade game that scores range from 0 to 20. Arcade has a set-up machine game tables that all contestants can play the game at the same time, thus contestant scores are independent. Each contestant's score will be recorded as he or she finishes, and the contestant with the highest score is the winner. Here's Josephine. So Josephine practiced the game many times, and here is her probability distribution for her score. So she either gets 16, 17, 18, or 19 points and this is the probability of each of those outcomes. And the same for another contestant, Crystal. And then part A says calculate the expected score for each player. Key word here is they don't use the word, keyword they don't give you is interpret. So calculating them is enough here. So when I scroll down to my solution, I calculated them and I showed the work. You multiply every x times p of x, add them up. I also interpreted, but that wasn't necessary, so it was a little extra in both of these. And to be essentially correct, you just needed both correct expected scores and work. So you could have used the formula. So simply writing summation of x times p of x was enough. Or you could have actually showed the calculation. In part B, they say, suppose Josephine scores 16 and Crystal scores 17. The difference in their scores, Josephine minus Crystal, is -1. List all combinations of possible scores for Josephine and Crystal that will produce a difference of -1 and calculate the probability of each. So it's a little bit more difficult, not so much figuring out the outcomes, because to get -1, you could be Josephine at 16 and Crystal at 17. That gives you -1. It could have been 17 minus 18 gives you -1. And then 18 minus 19 gives you -1. So those are your possible outcomes. And then the probability comes from, well, if Josephine got a 16, that was a 0.1 probability if I go back up here. So Josephine getting a 16 is 0.1. And Crystal getting a 17 is 0.45. So that means 0.1 times 0.45. That is the probability of getting Josephine getting a 16 and Crystal getting a 17. And same for the rest. The probability of Josephine getting a 17 in the original distribution was 0.3. And then to get -1, that means Crystal had to have a score of 18. That probability was 0.4. You multiply those and get 0.12, and same thing for 18 and 19. Josephine was 0.4 for an 18, and then that meant Crystal had to have a 0.15. So you multiply those two together, get 0.06. And then part C is, I did this on purpose because of scoring. Scoring was B and C together here. Find the probability, the difference of Josephine minus Crystal and their scores is -1. That just totals those probabilities up. So you just add those three probabilities. And then here is your scoring. I'll let you kind of do this on your own. I'll send these to your responses, but you can score yourself. And then I go into part D. The table below lists all the possible differences in scores between Josephine and Crystal and some associated probabilities. We all know these probabilities have to add up to 1. We just calculated this probability was 0.225 in the previous problem. So now to figure out our only missing probability, you would add these all up and subtract from 1. And that would give you this 0.085 that I filled in my solution. So this question was pretty easy. Even if you got this probability wrong, the 0.225, if you used it to get this one, they still give you some of the credit, and I'll show you that in the scoring. Wait, let me go on. Question's not quite done. So complete the table was part of that answer, and then you had to calculate the probability that Crystal's score is higher than Josephine's. So now you have to think about if Crystal's was higher, that means when you subtract Josephine minus Crystal, you needed negative numbers because Crystal was bigger. Right? If you have a small number minus a big number, or a small number minus a larger number, you're going to get negatives. So I'm interested in this table, what are my negatives? So that means what's the probability? Let me switch colors real quick. I'm running out of time. I need these probabilities. So what's that sum? So the probability that Josephine was higher than Crystal, Crystal was higher than Josephine was 0.325. And then the scoring, I'll send you this as well, is as follows.